Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The electron, seemingly a discrete particle confined by classical physics, defies such simple categorization. Its diffraction, an exhibition of wave-like behavior, demands a more nuanced understanding. Davisson and Louis de Germer's groundbreaking 1927 paper, The Scattering of Electrons, by a single crystal of nickel, presented compelling evidence for the wave nature of electrons, forever altering the landscape of physics. Their experiment, conducted at Bell Telephone Laboratories, involved directing a beam of electrons onto a single crystal of nickel and measuring the intensity of the scattered electrons at various angles. The setup, though seemingly straightforward, unveiled an unexpected phenomenon. The intensity of the scattered electrons exhibited distinct peaks at specific angles, resembling the diffraction patterns observed with X-rays passing through crystals, a phenomenon meticulously studied by Max von Laues some years earlier. This was perplexing. Particles, according to classical understanding, should scatter randomly. Waves, however, diffract predictably. The observation of these diffraction peaks suggested the electrons, despite their established particulate nature, could also behave as waves. This was a radical departure from classical physics, which treated particles and waves as mutually exclusive entities. Davisson and Germer's claims, bolstered by their experimental results, asserted the wave-like behavior of electrons and their capacity for diffraction. The intellectual groundwork for Davisson and Germer's experiment lay in the earlier work of Louis de Broglie. In 1924, de Broglie proposed his revolutionary hypothesis: all matter possesses wave-like properties. He posited a relationship between a particle's momentum and its associated wavelength, expressed by the equation wavelength equals Planck's constant divided by momentum. In mathematical terms, it reads wavelength equals h/p. Here, wavelength is represented by the Greek letter lambda, Planck's constant is represented by h, and momentum is represented by p. This hypothesis, initially met with skepticism, provided a theoretical framework for understanding the wave-particle duality of matter. Davisson and Germer's experiment provided the first empirical evidence to support de Broglie's bold claim. The observed diffraction patterns could be explained by assigning a wavelength to the electrons, calculated using de Broglie's equation. The angles at which the diffraction peaks occurred corresponded precisely to the predicted wavelengths, validating de Broglie's hypothesis and ushering in a new era of quantum mechanics. The influence of Max von Laues' earlier work on X-ray diffraction by crystals, specifically his 1912 discovery of the diffraction of X-rays by crystals, shaped the interpretation of Davisson and Germer's experiment. Laues' work provided the theoretical tools for understanding diffraction patterns. He demonstrated how the regular arrangement of atoms in a crystal lattice could act as a diffraction grating for X-rays, producing characteristic patterns of constructive and destructive interference. Davisson and Germer recognized the analogy between their electron scattering results and Laues' X-ray diffraction patterns, using Laues' framework to analyze their experimental data and deduce the wave nature of electrons. Consider, for instance, a specific diffraction pattern observed by Davisson and Germer. A strong peak in electron intensity appeared at a scattering angle of 50 degrees when accelerating electrons through a potential of approximately 54 volts. This peak corresponded to a wavelength of approximately 1.67 angstroms. This value aligned closely with the wavelength predicted by de Broglie's equation. Given the momentum of the electrons at that accelerating voltage, a similar X-ray diffraction pattern from a crystal might show analogous peaks dependent on the X-ray wavelength and the crystal's lattice spacing. The immediate impact of Davisson and Germer's experiment resonated profoundly within the scientific community. It firmly established the concept of wave-particle duality, demonstrating that electrons, long regarded as particles, also exhibit wave-like properties. This finding formed a cornerstone of quantum mechanics, solidifying its foundations and opening avenues for further exploration into the bizarre and counterintuitive realm of the quantum world. At a stroke, the experiment cast aside classical intuitions concerning the fundamental nature. The subsequent section will delve into the theoretical interpretation of these diffraction patterns, contrasting the experiment's results with de Broglie's equations. We will explore the role of the crystal lattice in modifying the electron wavelength. Finally, we will shed light on the development of electron microscopy, which employs live nature of electrons to achieve resolutions far exceeding those of optical microscopy. The observation of diffraction patterns in the Davisson-Germer experiment demanded a profound shift in theoretical interpretation. The experimental results aligned remarkably with the predictions arising from de Broglie's hypothesis, offering quantitative verification of the wave nature of electrons. De Broglie proposed that the wavelength, lambda, associated with any particle of momentum, p, is inversely proportional to that momentum. This relationship is expressed as lambda equals h divided by p, where h represents Planck's constant. In the context of the Davisson-Germer experiment, the accelerating voltage applied to the electron gun determined the kinetic energy of the electron. Consequently, specifically, an electron accelerated through a potential difference, V, gains kinetic energy equal to eV, where E is the elementary charge. Relating this kinetic energy to momentum yields P equals the square root of 2mEV, where m is the mass of the electron. Inserting this expression for P into de Broglie's equation gives lambda equals h divided by the square root of 2mEV. Calculating the de Broglie wavelength for the electrons used in the experiment, given the accelerating voltages, and comparing these wavelengths with the observed diffraction angles provided compelling evidence for the wave nature of electrons. Precise measurements of the diffraction peaks revealed that the observed angles corresponded directly to the wavelengths predicted by de Broglie's equation, validating his hypothesis and showing that electrons behave as waves with a quantifiable wavelength. However, a subtle refinement became imperative. The electrons, upon entering the crystal lattice of the nickel, experienced a change in their potential energy. This inner potential of the crystal lattice, typically on the order of 10 to 15 volts, altered the kinetic energy, and, therefore, the momentum or wavelength of the electrons within the accounting for this inner potential was essential for achieving precise agreement between the experimental data and de Broglie's theory. The wavelength inside the crystal changed to lambda prime equals h divided by the square root of 2me times the quantity v plus v naught, where v naught represents the inner potential. This refinement demonstrated the importance of considering the interaction between the electrons and the crystal lattice in understanding the diffraction patterns. The Davisson-Germer experiment delivered a powerful blow to the classical conception of electrons as solely particulate entities. The observation of diffraction, a phenomenon intrinsically associated with waves, indicated that electrons exhibit both wave and particle characteristics. This discovery cemented the principle of wave-particle duality, a cornerstone of quantum mechanics, forever altering our understanding of the fundamental nature of matter. The experiment's repercussions extended far beyond its immediate findings, profoundly influencing subsequent developments in physics and technology. A notable example lies in the development of electron microscopy, a technique that leverages the wave properties of electrons to achieve resolutions far exceeding those attainable with optical microscopes. Optical microscopes, limited by the wavelength of visible light, can resolve details down to approximately 200 nanometers. Electron microscopes, however, utilizing electrons with wavelengths thousands of times smaller, can achieve resolutions on the order of angstroms, permitting the visualization of individual atoms. Transmission electron microscopy, or TEM, relies on transmitting a beam of electrons through an ultra-thin sample. The electrons interact with the sample, scattering in ways that depend on the material's density and composition. The scattered electrons are then focused by electromagnetic lenses to create an image on a fluorescent screen or a digital detector. The resulting image reveals the sample's internal structure at a near atomic level. Its impact is difficult to overstate. Furthermore, the Davisson-Germer experiment left its imprint on the development of quantum field theory, or QFD. In QFD, particles are interpreted as excitations of quantum fields, rather than as fundamental point-like objects. This framework elegantly incorporates wave-particle duality, describing particles as wave packets propagating through their respective quantum fields. The experiment served as empirical bedrock, bolstering the conceptual foundations upon which theorists built QA. The experiment holds enduring relevance. Electron diffraction techniques continue to be used extensively in materials science to probe the crystal structure of materials. Techniques such as reflection high-energy electron diffraction, or RAID, and low-energy electron diffraction, or LEAD, exploit the diffraction of electrons from the surface of materials to determine their atomic arrangement and surface properties. Concluding, the Davisson-Germer experiment stands as a pivotal moment in the annals of physics. Its findings solidified wave-particle duality, revolutionizing our understanding of the fundamental nature of matter. The experiment paved the way for countless subsequent discoveries and technological advancements. It remains a testament to the power of experimental investigation in challenging established paradigms and advancing the frontiers of human knowledge.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.